That's right.
Oh, look, thank you very much, Valerie. And I think we'll catch up with time. I think it was really important to have that broad coverage, because we'll have to get a copy of your presentation, Valerie, because there's a lot of stuff in that that matters to this community and sets the scene for the day. So wonderful, thank you very much. Now I'd like to invite Roderik van der Waal to take the stage and talk about what Valerie preempted, high-end sea level estimates.
Okay, it's not an easy task to talk after Valerie, I think, but I'll do my best. And well, I think life continues after AR6, and I'll have some ideas on how we should do that in the IPCC sea level framework context. So I think in that sense, it's a good order of our presentations. So what I will do is I will give a presentation here on behalf of the WCRP Grand Challenge team, which does not exist anymore, but it's a group of people who have been working on sea level change issues over the last 10 years, I think, about. And those with the red dots on the close to their face, they're in the room. So if you have difficult questions afterwards, I suggest you not raising them to me, because I'm just the messenger. And you can go and find them in the break. So if you are very fast, you will also realize that there are no AR6 sea level chapter authors in this group. So this presentation leans very much on work which we published last year in Earth Future, a high-end estimate of sea level rise for practitioners. And I think I would like to start, in fact, with another paper which was also published last year, but maybe less known to everybody in the audience here. And that is a paper where M.A. Slange tried to make a summary of what we know about sea level rise in the course of the IPCC reports over time. And what it does here in this figure is that it compares the sea level projections starting from AR5, so that's 213, moving to SROC 219, and then AR6 221. And if you look in this figure, you can see that the global mean sea level rise projections did not change over time. So global mean sea level projections are a done case, I would say, for the 2.6 scenario, also for the 8.5 scenario, as long as our interest is in the likely range, so close to the median projection. And that does not only hold for the global mean sea level contribution, but it also holds for the individual components which contribute to sea level rise. And the trick, of course, is that there are people interested in the median projections, but many people are interested in the tails of the distribution of the projection. And there you see that with the gray bars, there's still some dispute on what is the right value and how we should interpret that value. Also on the regional scale, there is still dispute if you compare the AR5 RCP 4.5 scenarios and the AR6, then you can clearly see that there are differences. So it's not that we know everything about sea level, but there's a great deal we know about sea level in terms of projections. But the tricky thing is how we should discuss the high end of the trend. So this is not about extremes with the waves and the surges, but this is about the slow, gradual increase, and then not the likely range of this projection, but the tail of the distribution. And that's what we call the high end. So it's somewhere in the tail, but we do not assign a probability to it. Sometimes it's called worst case, but I think that's a bit misleading term, because the worst case is that you melt Antarctica overnight, and then we all know what the sea level contribution will be, but we also realize that this is not going to happen, so it's not a very useful result to present to practitioners. But they still need a value which is possible, plausible, but not the worst case. That is where the high end comes in. And of course, we are all here because we know something about Antarctica, and the high end is very strongly related to the large uncertainty in the ice sheets. I say it in plural here. We didn't talk about Greenland much in this meeting, but also the Greenland ice sheet plays a role in the uncertainty in the high-end estimate. And what you see here is a small animation. It's kind of plug. There's no poster on it, so don't worry, you don't have to look for it. But it's one of our new ice sheet models which we developed, which if you look carefully is based on triangles. It's an adaptive grid, and it changes over time, so it allows different approaches for near future simulations. Euphemism, we call it. So an attempt for a definition of a high-end. I think a high-end sea level projection uses multiple lines of evidence, and it has the physical plausibility to constrain the estimate of critical processes contributing to sea level rise. And it's not a definition I came up myself with, but the whole process here, I did not say that at the first slide. It's a co-creation between practitioners and scientists. At least, I would say that was the aim of the process. If you recall the first slide, you saw that practitioners was a little bit smaller than scientists. So I think there's, in this process here, still a bias to the science approach, rather than really the co-creation in an equilibrium. But I guess it's the first step we made. So we know it's in the tail, but we cannot precisely define the probability of it. Of course, in simple words, if you don't like definitions, how much sea level rise and when. So what could be solutions to address specifically this high-end sea level rise? Well, the most logical thing some people may think is use Earth system models, and you calculate that because you have a lot of Earth system models, but they don't have explicitly the ice component in it, so that doesn't work. Deterministic ice sheet models, that is where we heard a lot about this week, and there's a lot of people working, like the ISMIP people, and they usually have some output forcing from a GCM, and then they calculate the response of ice sheets, and that's, I would say, maybe the traditional way, which is hampered by the fact that there is an agreement that the physics of ice is poorly understood, so maybe you don't get a good idea on the high end. So the probabilistic approach has been used to address the tails of the distribution just to get the full PDF of sea level rise projections. This has been explored, say, 5-10 years ago, mainly, in papers like the one by Bob Kopp and Davy Lebar. But there you simply assume a certain a priori contribution from Antarctica and then make your probabilistic approach. So that's not the right way to do it, because you put in a priori information, which is in the end controlling what you get out in terms of the high end. Another approach which has been explored in two papers, actually, one from 2013 and one from 2019 from Jonathan Bamber, based on the idea that experts do a better job in predicting things which are difficult to predict, like earthquakes and volcano eruptions, and then trying to use these techniques also to make projections for sea level rise. This is, from a practitioner perspective, also not very attractive, because it's not transparent. You don't know what the people in the group thought when they made their projections, and there's always the argument whether this depends on the group of experts or not. So it's also not a satisfying approach. I'll come back to this. And then there are some plausibility approaches which have been explored in the past, but they also assume a kind of ad hoc acceleration of sea level, for instance, in the work of Ted Pfeffer in the 2008 paper, which more or less set the scene for this kind of work. So ad hoc is also not really satisfying, I would say, so that's also not a very good or final way to approach this. So let's first go to what has been done in AR6, and I think this figure has been shown a couple of times during this week, and this is the high impact, low likelihood scenario of the AR6 report. And in that sense, I think the AR6 report did a good job, in the sense that it's an explicit, in gray, I think you can see. I don't think it's very transparent. It's probably quite difficult for most people in the audience here even to understand what is underlying this approach. So That's a little bit a difficulty with it, I think, and if I may have some further criticism, I think it's also suffering a little bit from a thorough assessment, which should be the case in an IPCC report. So this is not recorded. But we're talking about this 2 to 15 meter range, and I think it should be our goal to limit that range at least in AR7. Because 2 to 15 meters is really enormous, of course. But this transparency issue, I have to admit, is reasonably solved in the meantime, because there's a paper from Bob Kopp explaining how they came to all these scenarios. So if you really want to understand what happened in the IPCC report, I think you have better first read the paper by Bob, and then you have a better understanding on how it works. But I'll explain it also a little bit, because I think it's illustrative to realize and to learn to value this 2 to 15 meters. So what they do in AR6, that is that they have workflows to get to an estimate of the high end. And if we start with the lowest line, the orange line, is there they take ISMIP, so the G is Greenland, the A is Antarctica. So they take, for Greenland, the approach from ISMIP, for Antarctica, they take the AR5 approach. So that provides you the lowest high end or hill scenario. If you change then the Antarctic contribution to the LARMIP approach, so that's a single paper, which is based on linear response theory, and I'm a co-author on it. There are a few co-authors, I think, in the room, but I think it's fair to say that this paper is not generally accepted in the community. But if you do it, you get the red line. Then there is the structured expert judgment. If you use that both for Greenland and Antarctica, so it's also a single paper, the Bamber 2019 paper, you get to 12 meters. And I think there are many people who have doubts by that approach. And then in the end, if you replace, or you still take ISMIP for Greenland and you take DP21, and it's of course a pity that Rob is not here, that's the De Conto and Pollard 2021 paper, then you get to the values which justify the statement that it may be more than 15 meters in 2300. And I think this paper is often a bit misquoted in the sense that the very high values of the paper are attributed only to the fact that he includes marine ice cliff instability. But I think we have to be a bit careful in saying that, in the sense that it's not just marine ice cliff instability which makes these high values. It also depends very strongly on when the major ice shelves collapse. And I'll come back to that point. And I'm not saying that it's wrong, but I think that's a critical point where we should focus attention to in future work. So what are alternatives? And I'm not saying that it's better, but it's at least another way of thinking. And that has been proposed by Ted Shepard in a paper in 2019. In fact, focusing not on sea level, but on climate change impact studies in general. And that is the storyline approach, which we now come across in many papers, I would say. And that's framed in this context as the identification of physically self-consistent. And I don't dare to use the word plausible anymore, because I've been criticized recently on what plausible means, but I leave it for that for the moment. And that means that you focus more on what the impact is of your result than rather what happens. So, and then again, realize that this is should be a co-creation between practitioners and sea-level scientists, because the high end is something which is used by practitioners. It's what they need, so they also have to say what they need and why they need that and how we can accommodate that question. So in the ideal world, that should be a balanced thing, but we are here on a meeting with all kinds of scientists. Maybe a few feel that they are practitioners, but it's not true that next week there will be this room filled with practitioners. This community is not really organized. So it's very difficult to get a view on what practitioners need on a global scale. There is a practitioner working in the harbor of Trieste who has his ideas, but he's not talking with a practitioner in the harbor of Rotterdam. So it's difficult to get a view on what practitioners need. But if we look to this storyline approach, and that is a figure which was shown by Valerie, which is in this paper, you consider all the different processes which are relevant for the Antarctic contribution to sea level rise. And that's a lot, and there is a lot of confusion on these processes and also on how they interrelate with each other. And if you look carefully to this figure, you see there is climate sensitivity, there's emission scenarios that leads to temperature changes, and these temperature changes are, of course, specific in Antarctica and in water temperature and in ocean temperature, which is both relevant for Antarctica. And in the end, it matters for surface melt, hydrofracturing, which is critical for ice shelf breakup, the bottom melt, basal melt, below the shelves, and the calving, which are all in a combination of processes relevant for the existence of ice shelves. But as long as we have ice shelves, is my view, we cannot have a very rapid acceleration of mass loss in Antarctica. And it's just after these ice shelves are gone, then we have all these complicated dynamical processes, Mizzy, Mickey, sliding, which are all very unconstrained, which determine the rate of sea level rise. But the timing of the sea level rise is controlled very much by the breakup of major ice shelves. And it's not one ice shelf. We even don't know which ice shelves are the most relevant for that and on what time scale we get the sea level rise. So I think, as a community, we should have a little bit more attention for that and focus a bit more on ice shelf breakup rather than only focusing on the dynamical processes. Not sure everybody likes this, but my view. So I think that could be a way out for future work and get better results in AR7 than what we had now. So if you follow the entire approach, you dig in the literature and you see what supports the different scenarios which we took, the low scenario 2.6 and the 8.5. As a high scenario, 2 time scales, 2100 and 2300, we come to the different contributions of sea level rise as you see them in this table. And I'm sure you cannot digest that rapidly. But there's one thing I would also like to draw your attention to, and that is that if you take this approach, it's not trivial how you assume that the different components are correlated to each other. It's not for sure that if the Antarctic contribution is high, the Greenland contribution will also be high. There's overlap in the processes, but there are differences in the climate change, and hydrofracturing is maybe not that important in Greenland as it is in Antarctica. So it's not very trivial how you should add up the Greenland contribution and the Antarctic contribution. And this is a bit underestimated, and it's under the carpet in AR6 also a bit, I think, because of the use of emulators, which are essentially temperature-driven, but the processes are very different between the different ice sheets, so you need to be very careful in how you deal the summation of the different contributions. So, the IPCC versus what we did here. If you look to 2100 and you look to the 2-degree scenario, I think there is not very much difference between the two approaches. The 2100 plus 5-degree scenario and the next one, the 2300 plus 2 scenario, they differ considerably, I would say, between this approach and the IPCC approach, mainly due to the Greenland contribution. So that is driven by this SEG inclusion in the AR6 work. And for 2300, we end up with quite a bit lower value for Antarctica for the high scenario because we average out the Continent-Pollard paper with other studies which are around in the literature, which we average, and then you get a lower number. And that is because we would like to use multiple lines of evidence rather than relying on a single paper, which is in the end what happens in this workflow approach in the AR6. So the alternative which is presented in this paper, I think it's at least transparent. It's a very simple table explaining how we combine the different results. It's a physically based approach, and yeah, unfortunately, you may think that that excludes the structured expert judgment paper. It uses multiple lines of evidence, so we take whatever is available in the literature, although I think we did at the time of writing, of course, which is now already 1.5 years ago. But in the bottom line, and the fact that we did it like that, provides it greater practitioner value. And that's not what I think as a scientist, but that is what practitioners tell me. And I think that's an important notion, and I think we should be aware of that. And in future attempts, we should really try to take that also as a starting point to get to a high-end value. So in the end, there are large differences in adaptation efforts between 2 and 5 degrees in 2100, and that could not be a surprise to you. So in that sense, the bottom line of the message is not changing, I think. Beyond 2100, I think the bottom line is that there is an enormous difference between a low and high scenario for the high-end sea level rise projection. It should also not be a surprise to you. But I think in that sense, these are key messages which you can convey always to practitioners. And if I listen back from the practitioners, adaptation is feasible at many places for a 2-degree scenario, beyond 2100 also. So that please, I would say, for strong mitigation measures. And is 2-meter global mean sea level rise unrealistic by 2100? A question which has been out in the community and in society also. I think yes, it's unlikely, but locally we cannot exclude it, I think, because the local sea level rise may be a bit higher, not very much in most places, but say 25–30% higher than the global mean values. So that's my conclusion. And I was not warned that I run out of time. So maybe as a teaser for further discussion, I also have a slide on the discussion. What are the open ends in my view? I think this did not address intermediate scenarios. And there was a good reason from a science perspective not to do that, because there's very limited studies taking the middle road. And I think I had a brief chat before this presentation with Valerie. The reason is that there's fair agreement that for 8.5 we have collapse of major ice shelves, but in fact we are not sure whether that is the case for 4.5, 2.6, or maybe already committed. There is a gray area, so we really need to dive into that area in more detail in future, I think. There's also a request from practitioners for the 250 and 2.2, which we did not address. Well, I think that's a technicality which can be solved. And of course, this was constrained to the global mean value, and there's no practitioner interested in the global mean. They want to know what's happening in Trieste or what's happening in Rotterdam. So providing a tool to translate this to the local situation is the thing which needs to be done. And that's, in fact, it's picked up already. There will come a paper soon doing this for the UK, I think. And I think that may serve as a standard to do it, to make the translation. But the big question, of course, I think is where are the physics not sufficient and when do we need expert judgment? Because there's underlying expert judgment in this approach as well. I mean, it's not free of ambiguity. And I think that's a discussion we should take up as a community. Which processes, which scenarios, or which timescales do we have enough confidence in our models to address the high end from a physical perspective, and where do we need to make expert judgment. And then, of course, the issue is we did this with 32 people, maybe we're biased, so how do we prevent bias and try to get this as a community vision? And I think that would be very helpful if we manage to do that for AR7.
Thank you, Rob.